I welcome you on the second lecture on seismic response of pile foundations. In the first lecture, we already talked about introduction, basic concept and Seismic theory. Today, we are going to talk about Novak's 3D model, which has been already introduced when we talk about introduction, and there are two papers. First one in 1976 by Nogami and Novak, and the second one by Novak and Nogami in 1977. And after that, we are going to talk about solution given by Novak in 1974 and finally Gestalt. So, let us start from this Novak's 3D. So, we are going to start from this point and continue with this. So, in this theory, analysis performed separately for vertical and horizontal mode of vibration. So, this is basically similar what we have discussed for Seismic theory. Seismic theory was only for horizontal vibration, and they have proposed for thus both axial vibration and horizontal vibration also. That however, separately, that means there is no coupling between these two. So, when vertical mode of vibration is considered, horizontal displacement is neglected and vice versa, and the coupling between two modes of vibration has been not considered in this theory, and the theory assumes soil as a linear, elastic, homogeneous and isotropic layers with frequency independent hysteretic type material damping. So, there is a now difference is there. So, naturally the question may arise that then what is the difference, because horizontal both mode of vibration are considered separately. Even for horizontal mode of vibration, there is a basic difference between Seismic and this theory, that the Novak they have considered hysteretic type material damping, which is more applicable for the soil. So, this is important. The damping type of damping is different, and the damping considered by Nogami and Novak is hysteretic damping, not the viscous damping as considered by the Seismic. So, for horizontal mode of vibration, this theory is the same as given by Seismic, except that in latter case viscous damping is considered. That means, viscous damping is considered by Seismic, however, the hysteretic damping is considered by the so we already discussed. Thus, in the absence of material damping, both theories are exactly the same for horizontal vibration. If we neglect the damping in Seismic theory and this Novak theory, actually this is like this. 1976 is for vertical vibration. So, 1977 is for the horizontal vibration. So, if I consider this horizontal vibration and neglect the damping, then both Seismic theory as well as this Novak becomes same. So, continue with this. Now, let us talk about that it is in the same fashion. First you consider the complex soil stiffness and then you consider the complex pile stiffness. So, let us talk first by vertical vibration by complex soil stiffness, and for vertical vibration the earlier displacement u was considered for the horizontal direction, but now for vertical vibration here Wn is considered, which is for the vertical vibration, and other equation is similar, and instead of now alpha n is considered, again you can see that this is a function of z. That means, the displacement is varying along the depth, and n is representing again the mode of vibration, where the known and dimensionless resistance factor alpha n in this theory is given by the relation here, when k1 and k0 are again nothing but Bessel functions of this is 0th order and this is the first order Bessel function. Qn is given from this relation, and in this relation Hn is coming, which is given by this relation, where Hn is related to the mode n. When you vary the value of n, the Hn will vary, where value of n is 1, 2, 3, and eta, which is the ratio of Vl by Vs, that is the two velocity, one is for in the longitudinal direction and the shear wave velocity. So, this is given from this relation. So, in equation Qn you have everything here except dV and ds, which are damping. dV here and this ds is damping ratio for volumetric strain, volumetric direction and shear. So, these are defined here. In the above equation, they are the hysteretic damping ratios associated with the volumetric and shear strengths respectively. So, this equation number 3a to 3e gives you basically the complex soil stiffness when you do not consider the pile. Once you insert the pile inside the system in that case what you will have and let me like that for you can refer this slide for this actually this slide which we have already discussed. So, this slide is also this is applicable for the Novak theory also. This is for axial vibration, the first one, and the second one is for this second one is for horizontal vibration. So, with the continue with this. So, what you have, the complex stiffness of the soil pile system for vertical vibration is given in this form using equation 4a, and you can see the equation 4a is how compact the equation. However, the equation 4a looks very small, but the value of k bar to be obtained need to be from this equation. Again on this equation hn bar, lambda bar and these are given here. However, you need to understand that all the things are known in this equation, because Hn is already defined, Hn has been defined. Once you know that let us say if we select the value of n equal to 1, then it will be simply pi by 2 h, and then capital H is known, lambda bar you can obtain once the properties of the E is Young's modulus of the pile here, okay, and nu is the Poisson's ratio. So, once these properties are known, then lambda bar can be obtained, then factor gamma can be obtained, and as a result ultimately you are able to get the value of k bar. Once k bar is known, and k bar is again we need to understand this is dimensionless stiffness parameter, there is no dimension of k bar. So, the stiffness dimension is E A into R naught, where E is Young's modulus of pile and A is the cross sectional area divided by the radius of the pile. So, this equation is very compact to find the value of k, stiffness of the pile, and naturally this stiffness will keep varying with the frequency. This is not going to be constant, that is point to be noted. It is a function of omega. This was the case for the soil also, this was depending on the omega, and here omega is coming in this here, this is coming in this case to find the value of Qn. So, that means at the stiffness of the whether you can say complex soil stiffness or whether you say complex stiffness of the soil pile system, they are frequency dependent. So, that is the issue need to be understand, that as frequency changes their values are going to change, and this was for vertical vibration. Same thing has been extended for horizontal vibration, where the equations becomes a bit longer than the earlier. So, this is similar equation which we have discussed for the TASMI, and only the thing that now you have this UN that is for this amplitude in the for horizontal vibration. Alpha Hn is given from this relation, where Tn is given from again from this long equation. In this long equation Qn and Sn is coming. There is a one basic difference here, like if you see that yeah. So, in these equations when we talk about vertical mode of vibration, the Poisson's ratio is not coming in picture, but here you will get the effect of because Qn and Sn, yeah, 1 minute. So, dV and ds, yeah, okay, all right. So, this will be in both the cases. So, this because if you consider but if you consider the isotropic, then in the conditions, then dV and ds, that is the static damping ratio, may be normally considered the same in both the directions for both volumetric and as well as shear strength. So, for the horizontal vibration, this the equations are given here, Qn and Sn is also given. So, everything, so we can find using equation 5a, we can find the complex soil stiffness, and when it is again extended for complex pile head stiffness. So, for this case it is possible to get the pile head stiffness in closed form, but it can be derived from the expression for lateral displacement after applying boundary condition to determine unknown constant as needed to calculate horizontal rocking or cross stiffness. When we talk about horizontal vibration, then along with horizontal there could be, we can have unknown needed to calculate, this same can be used for horizontal mode, rocking or cross stiffness. Expression for lateral displacements is given by 6a, where lambda is given by 6b. In this equation 6a, a, b, c and d are integration constants, and which can be determined by using the boundary conditions, while f1n, f2n, f3 and f4n are dimensionless functions, and these functions have the argument lambda z, where lambda is given, and lambda is basically representing your frequency. As omega varies, lambda will be varying, and into a Fourier sine series of argument h and z, and thus known. So, that means everything is known, you can using 6a you can relate the displacement on the left hand side, and on the right hand side you have the frequency and other parameters, and then you have this alpha Hn, which is the loading which we have already given. Alpha Hn is given from equation 5b. So, you can find the what is called the horizontal displacement for the pile case here. So, and EI is coming here, flexural rigidity of the pile. So, the properties of the pile is going to come. Naturally, one thing you need to understand, when you are dealing with complex soil stiffness, the first part, no property of the pile will come in picture except its geometry. That means, E is not required, that is what is Young's modulus of the pile, or what is the material property of the pile. Of course, because the dimension of the pile is required to calculate, that is R naught, or making the dimensionless frequency A naught. And one more thing which is important from very beginning. So, I think that has been like okay, we will discuss later also this thing. So, continue with this. Now, whatever we have discussed so far different, let us have a little comparison before we go ahead. There are a list of simplified approaches, but this slide gives you this is like and this slide is coming from the paper which I mentioned. This is let us say that Maheshwari and Watanabe. So, this is coming from, so this should be written, this is not like the new work, this is Maheshwari already published, Watanabe. So, this is 2009 publication. So, this slide is from that only. So, what you can see that from this, that there are 9 theories has been from different researchers, starting from Polaz, Pengin, Tazmi, Novak and Novak. So, let me, what has been for Polaz in 1968, it was for pile group. However, consider only static loads in both directions means both horizontal as well as vertical direction, and this is applicable for floating pile. Soil is elastic, homogeneous, isotropic, solutions in closed forms. One can, these are the assumptions concept. Those theories which are applicable for floating pile, naturally they can be applied for end bearing piles, but those theories which are developed for only end bearing piles may not be necessary that they can deal with the floating piles. That one need to understand. At the same thing, suppose if any theory is developed for pile group, that can naturally that can deal with a single pile, it is obvious, but it is not necessary that theory which is developed for single pile will be applicable for pile group. So, Polaz was for a static case. So, major issue with the Polaz was static loads only. Then in Pengin 1964, it was for horizontal vibration only and pile group, end bearing piles was considered. However, lumped mass models was considered, difficult to incorporate radiation damping and inertia of soil. So, that is why this theory was, even though developed in 1964, but was not in the acceptable form. Then Tazmi 1969 was the first work on the pile dynamics, but it was on the horizontal mode of vibration and considering viscous elastic stratum, which we have already discussed in detail. Then Novak 1974, which we are going to talk, because we have not talked any theory yet for pile group. We have talked about for single pile, we have discussed about Tazmi and we have discussed Novak. So, Novak 1974 was the first on the pile group, though Pengin also on pile group, but there was limitation for pile group, and this was for horizontal mode of vibration and end bearing piles. Soil is modeled as a generalized Winkler soil model possessing inertia and capability to dissipate energy. So, what has been considered by Novak in 1974, it is okay for considering the radiation condition as well as inertial effect, though nonlinearity was not considered. So, this Novak 1974 was the first work on like considering the radiation and inertial effect, and later on has been extended by many of the researchers including Novak themselves. In fact, in 1976 and 1977, which was the latter work by Nogami and Novak themselves only, that was on single pile. This was both vertical and horizontal modes of vibrations that has been done separately, that is for end bearing piles, and this is rigorous method linear based on 3 dimensional wave equations. Static damping of soil has been considered by these researchers. Then plane strain soil model has been considered in 1978. All these like you will find the detail in this publication by Maheshwari and Watanabe. So, all these reference citations, the details of this can be find out in that paper. Then you have plane strain soil model. So, this was as both vertical and horizontal separately. it is for end bearing as well as floating piles, bedrock is at finite depth. Then later Belne et al. Has done for the single pile, and that is for both mode of vibration, vertical as well as horizontal, and only for end bearing and finite element to reproduce the soil around the pile and a consistent boundary matrix to simulate the far field. Nonlinear soil behavior can be considered. So, for the Belne start, so you can say the Novak's work was on the linear case, then Belne started considering the nonlinearity of the soil. Then Wolf in 1978 is for pile group, both vertical and horizontal, end bearing extended for floating piles. What they have done, that they have considered a soil column below the pile to extend. Extension of theory of Belne for pile group and for floating piles has been done by Wolf. And the last one, Kenya and Kozol, I think this was the first systematic work on pile group, both vertical and horizontal with full coupling has been considered, and end bearing as well as floating piles has been considered in this case. So, a very rigorous and versatile approach, 3D linear analysis fully accounts for soil pile interaction, soil pile interaction. So, this was, so we have already discussed two of them in this list, Tazmi and the Nogami Novak, and then we are going to talk about this third one now, Novak. So, let us discuss Novak 1974, and then we will have talk about one more simpler. So, this is what we are going to discuss is from a very famous paper by Novak in 1974, which is published in Canadian Geotechnical Journal, and perhaps this is the first publication on pile group for the systematic study considering the continuum, that means considering the radiation condition as well as inertial effects. So, in this case dynamic response of footings and structures supported by piles can be predicted if dynamic stiffness and damping generated by soil pile interaction can be defined. So, what was their objective? Their objective was that there is one side soil, another side is pile. So, the soil pile interaction, if that can be, this interaction effect can be captured in the form of what is called stiffness and damping, then those stiffness and damping can be used for further analysis in the same way as done for the shallow foundations. An approximate analytical approach based on linear elasticity is presented, which makes it possible to estimate the dimensionless parameter of the problem and to obtain closed form formulas for pile stiffness and damping. So, stiffness and damping, all components of the motion in a vertical plane are considered, that is horizontal as well as vertical translation, rotation of the pile head is considered. So, in this case it is coupling has been considered, it is not that like later on. So, initially they have done for separately for vertical mode and the horizontal mode of vibration, and then later on rotation has been also considered. The stiffness and damping of piles are defined in such a way that the design analysis of footings and structures resting on piles can be conducted in the same way as applied in the case of shallow foundations. So, whatever the solutions given by Novak, those solutions has been later on very much used for this, because they have given the stiffness, and once the the dynamic stiffness, so it can be used like a spring and dashpot. And this is one thing need to be understand, these dynamic stiffness and damping, when we say it is of piles, it is not only of the pile, actually this is for the soil pile system. So, that means idea is that later on the people have replaced the soil pile system with the spring and dashpot, and then rest of the analysis they have done like a structural analysis. So, the task has been made very simple. So, that is why this so it is Novak has been, as I mentioned earlier, also considered to be the father of pile dynamics in the world. So, so let us discuss his work little bit, which may be initial work on the piles. So, what has been done here, this is the problem given here. So, in this problem you could see that this is for what you have two cases, one is for horizontal vibration and here you have the rocking. So, when the pile is subjected to horizontal mode of vibration, here first of all what is this is end bearing pile. So, this is fixed here, and let us say we have considered that pile head is also fixed against the rotation in this case here, and it can move here translation. So, when you apply the horizontal displacement or load, so this is the horizontal displacement given by the some earthquake, or you can say whatever. So, this point move from here to here, but this remain fixed, and the u will vary along the depth. Naturally, the value of u is maximum at the ground, which is uh, and minimum 0 at the base. Okay. Now, consider the first case in which the pile is excited by horizontal translation of its head or lower end by rotation of its head in the vertical plane. So, here it is excitation for in this case is given by the horizontal translation, while here due to rotation. So, what has been done here, that pile head is moved, okay, but tip is not moved. So, as a result this is deflected like this. But in the second case there is no translation of the head, however head is rotated. So, as a result, so pile move while no translation motion. So, it remain here, but it get moved, rotation is there. So, this rotation is shown here, and again the pile tip there is no rotation here. So, this rotation will be also varying with the depth, and it will be changing with the depth. So, and this effect has been later on by the Novak. What in the first case, what is called horizontal translation rotation in the vertical plane. So, in the vertical plane this is horizontal translation and rotation, and considering this case, when a pile element dz undergoes a complex horizontal displacement, which is what is called uzt at height z, it will meet a horizontal swirl reaction. So, if this is the displacement, and basically our unknown is this, that what is the displacement when you apply some force, and if you know the displacement, then you know already for given force, if you can calculate the displacement. So, force divided by displacement will be your stiffness, that is the case here. So, what is done for given force for given displacement, the Novak they have suggested to calculate the force. So, this is the force, and if this force equation 1 will give you the force, and if I divide this force in equation 1 with the displacement, then you can get the stiffness. So, rather than going in that, most important is that in this equation which denotes a horizontal swirl reaction, which is basically force, in this case for this reaction SU1 and SU2 are coming, where SU1 is for real part and SU2 is for imaginary part. So, what is SU1 and SU2? That is the depends on the soil pile geometry and properties. So, in this equation G is shear modulus of soil, I is iota, which is you know that iota is nothing but iota square equal to -1 or iota root -1. Parameters SU1 and SU2 are functions of dimensionless frequency A naught, which is given by R naught omega Vs, and depend on Poisson's ratio nu. The real and imaginary parts of the complex functions is given by the equation 2, where you have equation 2 SU1 A naught nu, and this is given. So, what you can see that in equation 2, oh sorry, this G will not come here, G should not be here. So, this should be, because this is components of SU1 only. So, one thing is that SU there I have two component, one is SU1 and another is SU2. So, you have in these two components SU1 and SU2 both are functions of A naught and nu. What is A naught here? A naught is dimensionless frequency, which is defined here, where R naught is the radius of the pile, omega is frequency of excitation, and Vs is the shear velocity. A naught is a dimensionless frequency. So, SU1 and SU2 both will vary with frequency, but not only with frequency, they will also vary with Poisson's ratio. Okay. Then equation 1, this can be written as okay, this SU1 and SU2 is like this, and or equation what is here 2 pi G A. So, you have G this and then multiply by this. So, okay, yeah. So, what is done here basically, again G should be removed if we want to compare the value of SU1 and SU2. So, and then SU1 and SU2 like basically you solve this component here, and in this component they are divided into two part, one is real part and another is imaginary part. So, real part of this equation will give you SU1 and the imaginary part will give you SU2. So, ultimately the value of SU1 and SU2 are given by the Novak in the form of the chart, and as mentioned in this equation 2, they are function of A naught and Poisson's ratio nu. So, the chart is like before we talk about the chart, what is in this equation Q, Q is coming in this equation, and yeah. So, you have in this equation the value of A naught, H 1, and so these are given here. Here Q is 1 minus 2 nu divided by twice 1 minus x naught is A square root 2, which is coming here, x naught is coming, and yeah, Q is coming here. So, Q is here and then x naught is also here. So, value of Q and x naught are given by these relations, and Hn 2, which is Hn where n can be 1 or 2, is Hankel functions of the second kind of order n. So, the second kind, so this is when H basically this is second kind, 2 is denoting that, this 2 is denoting that both H, this is the Hankel function of second kind of the first order, and when you have this is 0th order. So, one is for kind of order n, when n is 0, so it will be 0th order or the first order. Equation 2 was derived by Barnow 1967. Parameters were calculated for several values of Poisson's ratio in by Bardugo and Novak 1972, and which polynomial approximations are given, and the parameters as are shown in figure in these figures. So, what you can see in this case that you have SU1 for two cases for nu, here nu is 0.25. So, this is the value of nu and this is the value of nu. So, this curve is for nu equal to 0.25 and this is for 0.4. So, you could see that the value of SU1 initially increases with the frequency, okay, then almost becomes constant, while the value of SU2, which is denoting the imaginary part for 2 Poisson's ratio, you can see they are increasing with frequency continuously. The next is for vertical vibration. This was for horizontal vibration. The Novak also continued with the vertical vibration. The dynamic reaction of the pile pertinent to vertical vibration motion of the pile can be obtained using the same assumptions for soil as in the previous case, that is same for horizontal vibration, and assuming further that the lower end of the pile is fixed, then pile the vertical soil reaction acting at height z of the pile element dz as given by Barnow and Novak and Bardugo in 1972. So, this is the equation. Equation number 3rd. What is the equation number 3rd? Equation number 3rd give you the soil reaction, and the soil reaction can be find out using G multiplied by SW1 plus ISW2 WZ det T. What you have here, dz will be cancelled out from both sides, this may be cancelled out. So, basically soil reaction can be found from this relation, where W is the displacement in the vertical directions. So, if you know SW1 and SW2, then you can set a relation between soil reaction and displacements. So, here again basic issue is how to get the value of SW1 and SW2, and SW1 and SW2 are given from equation 4 and 5, and in these equations Z naught and J1, which are function of A naught, are Bessel function of the first kind of order 0 and 1, while Y naught and Y1 they are Bessel function of the second kind of order 0 and 1. So, one thing is very important, you have SU1 and SU2. SU1 and SU2 was function of dimensional frequency A naught as well as Poisson's ratio, but SW1 and SW2, which are applicable for vertical vibration, they depends only on the dimensionless frequency A naught, but not on the Poisson's ratio, that is one thing. Second thing, while finding the value of SU1 and SU2, you get the what is called Hankel functions, that is H1 and H2, H0 and if you see here this equation, you get the H0 and H1, that is Hankel function, but while in the for vertical vibration you get the Bessel functions. So, Bessel functions are needed to calculate equation 4 and 5, while in earlier equation Hankel functions was coming, and SW1 and SW2 are also plotted as earlier in the same figure. You could see SW1 and SW2, and there is only one curve because they are not depending on the Poisson's ratio. So, with the Poisson's ratio they will not vary, the variation is quite similar to for the values of SU1 and SU2, and but the values are lower than the earlier values for the even without depending on the Poisson's ratio. Okay. So, this completes Novak the theory of 1974. Later on Gazetas in 1984 given a theory for end bearing single pile, and this is very practical. So, what I am going to talk is applicable for only single end bearing pile, but this will give you a concept which can be directly applied and easily can be applied without much computer programming, and that can be easily handled in the closed form solution. So, what let us Gajdas have proposed. So, a numerical study is presented of the dynamic response of end bearing piles embedded in a number of idealized soil deposits and subjected to vertically propagating harmonic shear waves. Results for both kinematic and inertial interactions are offered in the form of dimensionless graphs and formula covering a wide range of excitation frequencies and of crucial material and geometric parameters are considered. Practical aspects of the evaluation of the influence of piles on the effective seismic excitation of a structure are discussed, and a case history illustrates the usefulness of the presented results. So, Gazetas presented dimensionless graph, formulas, and then they have talked about a case history also. So, that you can study in the paper. I will give you reference of that paper that you can go through, but what is the basic concept I am going to discuss, rest of the things you can study yourself. So, Gazeta, what is the concept given by the Gazetas is given in this slide, and this is very good practical concept for soil pile interaction, or particularly of the single pile. See, this is a complete problem is given in figure 1, the part 1 of the figure. So, what you have? You have a pile, single pile, and here though it has been like that pile is appear to be this appear to be floating piles, but this is not the floating pile, actually this is going up to the end. So, this is end bearing pile basically. So, ultimately because this is the end product here. So, this is up to going to the end bearing pile, and this was basically the theory itself is for on end bearing piles. That means, the pile is having here at the end. So, what you have in this case, what is the problem? This is the excitation, this is excitation applied. So, this is UG basically, this appears to be G A UG. UGT which is coming, which is clear in this slide. So, what you have that UG is the amplitude of ground motion applied at the base, at the fixed base, and which may be due to your earthquake or which may be due to seismic excitation, which we call. A pile is embedded inside the soil as shown here. The length of the stratum is L, capital L, as well as the which is the same of the pile length. So, this is being end bearing pile. So, what you have in this pile, that this is you apply this motion and you get at the here u naught, this is little bit u naught here, okay. And once you got u naught, what is done here, total mass of the superstructure is considered on the top of the pile as denoted as m in this figure. Young's modulus of pile is Ez, Poisson's ratio nu for the soil is nu, mass density of the pile is rho, and damping ratio is beta s for the soil. What is done here, that the first step is called what is called free field analysis without considering any pile. So, free field analysis means you have a soil stratum, you apply at the fixed base some motion and you get the output at the top which is given. So, free field analysis will convert your amplitude UZ into u naught, this is the value u naught and this is UZ, okay. So, this u naught divided by UZ will give you the amplification ratio for a given frequency. After that, this is the second case here. In the second case, what you have kinematic interaction. For the kinematic interaction, what we do, we apply the same motion at the base and get in the presence of the pile, but when you are considering the kinematic interaction, you do not consider the mass of the superstructure as shown in this figure. That means, mass m is 0 here, and in the presence of the pile you get the response of this this point as a UK. So, now earlier it was u naught, now it converted into UK, UKT. That means, and then after that if I consider the inertial interaction of the pile, then for inertial interaction what you consider? You also consider the mass of the pile, mass of the superstructure on the top of it, and then find the response. So, how it can be dealt? Ultimately what this was the problem, Gajdas converted this problem into this here, where only the mass of the superstructure is considered and the motion applied to this mass is already found as a in this step as a kinematic interaction. And what are the spring constants? They are found using this analysis for dynamic impedance. For finding dynamic impedances of a soil pile system, what is done? You do not consider the inertial force or the mass on the top, number 1, and you apply the load at the pile head. At the same point you find the displacements. So, the load, whatever the forces applied by displacement, you will give the spring constants. So, this way the dynamic impedances are found. So, now we come on the formulation part of this one for this theory. What is the equation number 1? First of all, for a base rock motion, UGT is equal to UG expansion I 2 pi ft, where f is f is a frequency of excitation, and this will be, that means UG, what is the difference? This is time varying and UG is its amplitude, okay. And this UG is your applied amplitude. Then doing the what is called one dimensional amplification theory, which is one dimensional ground response analysis, and this gives you free field displacement, which can be like we have that has done lot of literature is available in the Kramer also for this. So, using this you find the displacement at the top U02, which is called the kinematic interaction, the free field response. So, the ratio of U0 to UG is given by this relation, where Q is given by this relation here, okay, and where Vs and beta s are the s wave velocity and hysteretic damping in the soil. Iota square is -1 as we discussed. If you do not consider beta s equal to 0, there is no damping in the soil, then this equation 1b can be simply converted U0 by Ug 1 over cos 2 pi FL Vs, which is referred as a that as a F1 omega, if you recall in the Kramer and ground response analysis. So, this is exactly same as the free field response, which tends to infinity at the natural shear frequencies of the stratum, that is when here Fn is varying 2n minus 1 Vs 4L, where n is 1 2 3. So, this was story was up to this point now was for free field response. Now, what happens if this free field response you do not consider any pile. When you consider a pile, then this free field response will convert to what is called kinematic response, and it will be different than the free field response. So, the kinematic response is represented by, because when you insert the pile inside the system, then at the same point where you are getting the free field response, at the same point you will not get the free let us say at the, that means at the same point at the pile head, it will get the translation as well as rotation. Even your applied force is only translation, but you get translation as well as rotation, and this translation rotation has the amplitude up and phi p, and both amplitudes are presented in the dimensionless factors, which is called interaction factors. So, this is called kinematic interaction factors. So, equation 2 gives you two kinematic interaction factors, one is for displacement, another is for rotation. Here, while getting the kinematic interaction factors, both response kinematic response has been divided by the free field response U0, okay. So, U0 is free field response. If the same factor is divided by the original ground motion Ug instead of U0. So, equation 2 and 3 are exactly same, except the difference that it is normalized with U0. In equation 3 it is normalized with the ground motion amplitude Ug, then in that case it becomes amplification factor. So, one is kinematic interaction factor, another is amplification factor. For interaction factor you use free field response, while for amplification factor you use the ground motion itself. R0 is d by 2 is the radius of the pile, which is so nothing need to mention. So, this was the Gazetas hypothesis, and what the Gazetas has did, they have presented the graphs or chart for kinematic interaction factors and kinematic amplification factors. So, rest of the things you can find in the the reference, in the first reference is listed by Gazetas, which is published in Soil Dynamics and Earthquake Engineering. And initial part of this these two lectures can be found in the paper by Maheshwari and Watanabe in 2009 in International Journal of Geotechnical Engineering. Novak in 1974, that what we have discussed, dynamic distribution damping of piles, has been published in Canadian Geotechnical Journals. So, you can go through these references. All three references are important, particularly the second one cover the Tasmi's and Novak's 3D model. So, the second reference will give you the complete detail including the table which we have discussed for the simplified approaches. So, with this I conclude today's lecture, and it was little longer than normal, but I thank you very much for your kind patience. And so, we have talked today about seismic response of pile foundations. Thank you very much. Thanks.